This is the second half of the crystallinity video. We talked about things like degree of polymerization, what affects that. Now we're going to talk about rate of crystallization. How fast a material that can crystallize, how fast it crystallizes. So there's two temperatures of a material, and all temperatures have these characteristics if they're semicrystalline. And those are the Tg and the Tm. The Tg is the glass transition temperature. So below the Tg, a material is glassy. And when it's glassy, there is no molecular motion on the local scale. When you heat it above the Tg, then you start to get molecular motion. So below the Tg, these are hard, stiff, brittle materials. No movement, no nothing, no motion. In order for things to crystallize, you have to heat it up above the Tg, so you have molecular motion. Chains have to be in motion in order to move next to each other to nucleate and then create crystals. So then there's the Tm. This is the temperature at which any of those crystals will melt. So over this point, there's too much molecular motion. They just want to be a liquid over the Tm. So if you're between the Tg and the Tm, you have the ability to crystallize. The thing about the Tm to remember is Tm increases as the degree of crystallization increases. So the more energy required to reach the Tm with higher degree of crystallinity. So the higher the Tm something is, the more crystalline it is, the higher degree of crystallinity something has if it has a higher Tm. Above the Tm, no crystallization exists, because above the Tm, the entire material is a liquid. Too much molecular motion that won't slow down in order to crystallize. So the way to get crystallization is to raise something above the Tg, but keep it below the Tm. And the longer a polymer chain remains between the Tg and Tm, the greater amount of crystallization is possible for that material. So nucleation and crystal growth both depend on temperature. So here we have the rate of crystallization on the y-axis, and we have temperature on the x-axis. So here is Tg, and here is Tm. The maximum rate of crystallization occurs at the average between these two, so Tg plus Tm divided by 2. That is the point at which you will have the maximum rate, or the fastest crystallization occurring. And this kind of depends on the material you're talking about. This is for a crystalline linear polymer, or a semi-crystalline linear polymer. For example, for polypropylene, the Tg is -10 to -20, and Tm is 150 to 175 Celsius. One thing to keep in mind is almost always going to be talking about temperatures in Celsius. It's a scientist thing. Inside the lecture hall or the laboratory, I'm thinking in Celsius. When I'm out there in the real world, so to speak, I'm thinking in Fahrenheit. But usually all of the temperatures I'm going to refer to here are in Celsius. So when you're looking at polypropylene, your Tg is -10, your Tm is 150. So this, if you have polypropylene, it's going to slowly crystallize at room temperature until you reach an equilibrium. Again, 21C is room temperature, and that is in between the Tg and the Tm. For Teflon, the Tg is -110 Celsius, and the Tm is 330 Celsius. So if it's at room temperature, in other words 21, it's going to very rapidly crystallize. So how far apart the Tg and Tm are also affects the rate of crystallization. Now, crystallinity in a semicrystalline polymer can also be controlled, and that is something that is important. Now, there are ways to modify your processing or post-processing to affect crystallization. So the degree of crystallization, crystal prevention, depends on a relationship between Tg and the polymer surface temperature. So if you're trying to prevent crystallization, in other words, you're trying to keep something clear or you're trying to keep it more flexible, you want to prevent some crystallization. So if you want to quench this by rapidly cooling apart to prevent that crystal formation, you have to keep the Tg in mind. If the glass transition temperature is greater than the surface temperature, then if you quench it, you'll prevent crystal formation. Well, why is that? The glass transition temperature is the temperature of the polymer above which you get motion. If your surface temperature is below that temperature, you don't get any molecular motion. It can't move around, it can't wiggle around to create crystals. So whatever you do to rapidly cool it to that below that Tg, it will keep it that way. And the biggest example is a polyethylene bottle. Polyethylene terephthalate, your PET that you can use to make bottles, that has the ability to be a semicrystalline polymer. But as we all know, a PET bottle is clear. So, Gene, you told us that if it's semicrystalline, it won't be clear. Well, what I didn't mention to you is the TG of PET and versus the surface temperature. TG of PET is well above room temperature. So you can extrude your paracins, quench them down to room temperature, and then you freeze out almost all of the crystallinity, resulting in a clear paracin that can then be blow molded into a plastic beverage bottle that will remain clear because it remains amorphous because the TG is above room temperature, above the service temperature. But, Gene, what happens if the TG is equal to or below the service temperature? See, there's your problem. If the TG is equal to or below the service temperature, you're going to get slow crystallization over time. Because again, if it's above the TG, molecules can move. And if they can move, then they can crystallize. So if you quench it, you're only going to delay crystallization, because if you hold it at the service temperature, it's going to crystallize over time. It may happen during a product is in use, and that can change its properties. And if a product changes its properties while it's in use, it may no longer be appropriate for the use in which it is being used, so you can get product failure. So how do you, so you can't, if it's above this, if your TG is below the service temperature, you're not going to prevent crystallization. So what can you do then? You can't quench it, because you're going to get some crystallization anyway. You can nucleate. That is something to speed up the process of nucleation, so you get predictable crystal formation and predictable properties. So I mentioned heterogeneous nucleation before. It's also called seeding. So you use a polymer that's similar to the base polymer, but it has a higher melting point. And that promotes high nucleation rates and high crystal growth rates. And that promotes a higher degree of polymerization faster, and then you can control the structure. So then, when you control the structure, you can predict the properties. You can also orient something, so use directional crystallization below the TM or cold drawing. This can help you create crystalline filaments, fibers, or sheets. The crystallization occurs only in the direction of the orientation, and this is used to produce high-strength fibers and films. There is some degree of orientation in PET bottles with blow molding. So you can get some, if you look at the bottom of a PET bottle, you can see some areas that are amorphous, and that is where you can get some crystalline formation because of what happens during the blow molding process. So, crystalline versus amorphous for part shrinkage. Part shrinkage is something that has to be taken into account when you're dealing with a semicrystalline polymer. With a semicrystalline polymer, these are affected by both the temperature that the material is at and crystalline shrinkage. So as the polymer solidifies, you get a little bit of contraction as it solidifies, but then crystal formation and improved chain packing lead to far greater shrinkage values than those of amorphous polymers. So what you end up getting in the finished part is 5 to 10 times the shrinkage of an amorphous polymer. Here's the problem. Only 85% of the shrinkage occurs within 24 hours. The majority of it will happen within the first week, but the remaining, that small 1%, which can make a big difference in your product properties, can take up to 3 months. 3 months! Think about how much warehouse space you would need to keep parts in a warehouse for 3 months so they can finish crystallizing. But there's a remedy to that. Now with amorphous polymers, your shrinkage values are much lower. Shrinkage occurs very, very quickly, and all of the shrinkage occurs going from cooling of the melt to room temperature. So 90 to 95% happens immediately after processing, and 100% is complete within 3 to 4 hours. So your processing tolerances for an amorphous polymer are much better than for semicrystalline polymers because of crystalline shrinkage in a semicrystalline polymer. So I mentioned that it can take up to 3 months for something that is semicrystalline to fully crystallize. But there's a way around that, and that is through the post-processing of step known as annealing. So it's totally normal to anneal molded articles to promote that maximum crystallization. And so you take the part and you hold it at the maximum crystallization temperature, and this forces an equilibrium where all of that crystallization can occur within about an hour. So you have enough molecular motion to get all the crystallization to change. So it results in changes to polymer properties, so molecular mobility, morphology, and physical and mechanical properties. You can get predictable mechanical properties in the finished part within an hour as opposed to 3 months. And so it is important to determine the effect in order to determine the optimum processing conditions for a polymer. So annealing can be a very useful step when dealing with semicrystalline polymer. So annealing can have a variety of different effects. Here we have mechanical properties. B is optical clarity, that's down here, and then C is surface smoothness. So this is annealing temperature at 1 hour, and so here's the 760 Celsius up to 1200 Celsius, and then the ultimate tensile strength. So if you held it at 760 Celsius for about an hour, you get up to about 760 to about 982. You get kind of the maximum tensile properties. You get the better yield strengths, and you get better and you get more moderate elongation. Also, you tend to get much more smooth surfaces. The higher temperature, you get a lot more bumpy surfaces. And then you see here the various temperatures give you different levels of optical clarity. So you can modify the appearance and the properties of a semicrystalline polymer by annealing either at higher temperature for longer time as well. So there are a couple different routes to making crystals. There's melt crystallization, which is typically what we're talking about when we're talking about thermoplastics that are made through blow molding, injection molding. Anything that where there's an extruder attached to it is typically melt crystallization. But there's also solution crystallization that I will talk about briefly as well. Melt crystallization occurs below the melting temperature and above the glass transition temperature. So you're holding it between Tg and Tm to get crystallization. And the van der Waals forces depend on the distance between parallel chain segments. So first you get lamella that form, real small crystallites. Here's some amorphous loops sticking out, but this is a representation of lamella. Then you make larger lamella and larger crystallites, but your growth rate of these crystals is suppressed by these kind of amorphous regions that show up at the end. So I showed this cartoon before, but it's these regions that kind of keep some percentage of amorphous regions within a semicrystalline polymer. Crystal growth occurs in the direction of the largest temperature gradient. So here we have a dendritic crystal, also known as a snowflake. So a dendritic crystal grows out from a center point in all directions. If you have a strong growth gradient that usually is unidirectional dendritic growth, this is so in other words, this is cooler than the center. If you have isotropic and static gradients, they get larger quasi-spherical aggregates rapidly, so you get, this is kind of an isotropic gradient, so you're cooling everything down equally in all directions. Spherulites, or these individual crystals, have a size anywhere between 1 and 100 microns, or micrometers. And these are often called Maltese Crosses because they represent, they look an awful lot like this, which is a Maltese Cross. And so if you look at this through cross polarizers, you get something, if you see this Maltese Cross pattern, it means you have a semicrystalline material. So that's melt crystallization. That's typically what's happening in material that's cooling down after it's come out of, say, an injection molder, a blow molder, or an extruder. But you can also crystallize from solution, and when you're making fibers, this is sometimes how crystallization occurs. In fibers, this happens oftentimes through solvent evaporation. So first you start out with a dilute solution, and the molecular chains that are present are fully dissolved in this solution, and they're just kind of hanging out as individual coils. They really don't know that any other polymers are present. And then you start to evaporate the solvent off in a controlled fashion. They start to get closer and closer together, and then you get to a concentration that is something approximating polymers in the melt, and then you start to get lamella forming. And then once the majority of the solvent is evaporated, you get the highest degree of crystallization, and you start to get spherulites forming. You can also get solution crystallization through precipitation. And so you use a solvent polymerization method. The solvent dissolves the individual monomers, but not the resulting polymer. And when you reach a certain degree of polymerization, as the monomer is building into polymer, the polymer falls out of solution or precipitates in its semicrystalline form. But polymers that you get by precipitation tend to be more amorphous, than those that are crystallized through solvent evaporation. So they reach a certain molecular weight and then they crash out of solution. So once they're in a solid form, they can't crystallize any longer. It's that solvent that provides them the necessary molecular motion to crystallize. And once they're too big, they fall out of solution. So they tend to be a lot more amorphous. So you have a larger amorphous fraction if you have a semi-crystalline polymer from precipitation. So this concludes the crystallization lecture, and both of these will be covered in your quiz 3B. So please look at both halves of this video on crystallization to prepare for your quiz. Thank you.